Climate's influence on master plan performance cannot be understated. Understanding its impact starts with understanding the local climate. There are many climate parameters that can influence the design process, but none as difficult to define and work with as wind. A typical way to represent wind conditions at a location is via the use of a windrose. A windrose shows the frequency of wind events for each direction. The direction always indicates where the wind is blowing from. It can also show other information such as wind speed or temperature and can be presented for a variety of time periods or seasons. For example, the windrose shown here is for Pudong Airport in Shanghai. Recorded data between 2004 and 2014 is presented. The compass is broken down into 12 wind sectors: north, northeast, northeast, east-northeast, and so forth. Winds blow from the north 9% of the time, and from the north-northeast approximately 7% of the time, and so forth. The colors are also show the breakdown of wind speeds. These can be correlated to the legend. Selecting an appropriate data source is critical to understanding the wind conditions at the site. The windrose on the left is for Pudong Airport, which is found to the east of the city center. Hongqiao Airport is to the west. The differences are quite striking. The directionality is approximately the same, but winds tend to be stronger in Pudong, which is not surprising since it is much closer to the coast. Windroses can also be generated for different seasons and periods of the day. Here we have plotted two windroses, one for summer on the left and one for winter on the right. There are significant differences. This provides valuable design insight for everything from natural ventilation to improving pedestrian thermal comfort throughout the year. The reason for the differences in wind direction are due to high-pressure systems over continental Asia creating offshore winds, while monsoons in the summer reverse that, creating onshore breezes. Seasonal variability has many different forms. In the case of Adelaide, winter winds tend to blow from northeast or southwest, but in the summer, winds tend to blow from the two southern quadrants. A very useful graph is the psychrometric chart. It is commonly used by HVAC engineers to graphically represent psychrometric processes. It is also useful in understanding different climates. Here we show the conditions measured at Jeddah International Airport. Each dot represents an hour in the dataset. The colors represent the 4 seasons, and conditions range from cool and dry in the winter to hot and humid in the summer and autumn months. On the other hand, Kuala Lumpur is located in a tropical climate zone. The limited temperature range and high humidity is evident year-round. Even small changes in location can cause large changes in climate. Here we again see the climate conditions at Jeddah International Airport. The conditions shown here are for an island just off the coast near Jeddah and will have a very different climate, as will a location in the mountains to the northeast. Sometimes weather data is not available or the quality of the measured data falls short of what is required for the project. This could be due to a variety of issues, such as the measurement station being too far from the project site, or that the site conditions differ significantly from the conditions near the meteorological station. In these cases, it might be required to synthesize a meteorological data file by using weather simulation tools such as WRF or weather research forecasting. This type of approach uses a computational model of the planetary boundary layer, which divides up the target area into small cells. These cells range in size from over 10 kilometers to less than a kilometer. This model creates detailed weather simulations which accounts for local topographical changes and land uses. In this fashion, multi-year meteorological files can be created, which can then be used in the absence of a local meteorological station. This type of modeling is also useful to test potential future climate scenarios. For example, since the forecasting model requires the user to provide a map of land uses, we can test the impact of urban sprawl on local climate. On the left, we see Abu Dhabi's urban footprint in 2006 in pink. On the right, we see the projected footprint for 2030. We expect a larger urban heat island impact as a consequence of the increase in city size. WRF modeling was conducted for two scenarios. The 2006 scenario represented the current city build-out at the time. The 2030 scenario projected a significant amount of urban growth. The model was simulated for every hour of the year. It should be noted that the only change between the two scenarios was that of land use. Emission scenarios and global warming impacts were not included in the simulation. The results show an annual average increase in dry bulb temperature of 2 degrees Celsius. An increase in dry bulb temperature of 7.6 degrees was simulated for a day in February. This level of change can have significant impact on building design.
Coming up in Module 4, Understanding the Built Environment.